So today we're going to be talking about horses.
So we'll start with a review problem from last week when we did 2D kinematics. And so we have a 510 Newton swimmer who dives off a cliff with a running horizontal speed at the top over there. What is the minimum speed so that she leaves the top of the cliffs and she doesn't hit the ledge at the bottom? The ledge is 1.75 meters wide and 9 meters below the top of the cliff. So we can give maybe 5 minutes, like around 12:15, and then we can reconvene. Yeah, we've given all the givens, unknowns, and kind of most of these will be found on the equation sheet. Some of these will not, but they can easily be derived from them. So hopefully you guys are able to solve it. This question is actually a little bit simpler than most 2D problems in that we don't have an angle. She just jumps horizontally off the cliff. And since she jumps horizontally off, we know that in the x direction, there's no acceleration, whereas in the y direction, there's a constant minus 9.8 meters per second squared, acceleration of minus 9.8 meters per second squared. And so all we need to find is, we know that she has to travel 1.75 meters to the right, and we know that she's going to fall 9 meters. And we know that distance in the x direction is velocity times time. So I'll just, can you guys see that? Is that a no mark?
I was just looking in the wrong place.
That distance is the x velocity times time. And we need to find the x velocity. We know the distance, and we also don't know the time. To find the time, we can use the y equation, which is y is equal to 1/2 at squared. So we know that it's 9 meters tall, and the acceleration due to gravity is minus 9.8 meters per second squared. So to find the time, we can just rearrange this equation, and we can get that it's 9 times 2 divided by 9.8. And then you take the square root of that whole thing, which turns out to be 1.355 seconds. So now we know the time is 1.355 seconds. To find the x velocity, we just have to divide the distance by the time, so that's 1.75 meters divided by 1.355 seconds, and that's 1.29 meters per second. Does that make sense? Is there anything else someone would like to add?
I would just like to say that what we're doing here is we're saying she wants to travel at least 1.75 meters in the time it takes her to fall 9 meters.
Yeah, thanks for clarifying that. So starting off with today, Mark, you're taking this one, right?
Yes, I am. Can you clear your annotations? Okay, so today we'll be talking about forces, but what is a force, right? A force is a special type of interaction between or on an object. When a force is unopposed, it will cause an object with mass to accelerate. There are two types of forces, those that involve contact and those that don't. So we have contact forces and non-contact forces. A contact force is a force that requires objects to be in contact with each other, whereas a non-contact force does not require contact between objects. A force is measured in newtons, and we'll talk about what a newton is later. So the basic forces that you'll need to know for this class are the gravitational force, which is in most cases just weight, which is given by m times g. It is a non-contact force. You can think of that as because you don't need to be touching anything to weigh something. You also have what's called a normal force, which is the contact force on an object that is perpendicular to the surface of an object it's in contact with. So clearly, just by the definition, we know that it's a contact force. And just to give you an idea of what the normal force is, we do have normal force here being directly up, but it might not always be directly up. If you've got an inclined plane and a box on it, sure, gravity is pulling it down this way, right? That's gravity, so we'll call it F sub g, right? But normal force isn't going to be straight up. It's not. it's going to be perpendicular to the inclined plane because we define it to be as perpendicular to the surface the object is in contact with. Does that make sense? Okay. We also have friction forces. A friction force is a force that resists the sliding motion of objects. And we'll talk about that more in a little bit. Friction is a contact force. There's also a tension force. Tension is this pulling force that's transmitted through something like a rope, a string, or a rod, or a spring for that matter. And an applied force is a force that is being applied onto something, onto an object. For example, if you're pushing an object, the force that you're pushing it with is going to be the applied force, as we can see in the lower left-hand drawing.
And so we're going to talk a little bit more about friction forces. There's two types of friction forces. There's static friction and kinetic friction. Static friction is the friction that keeps an object from starting motion. So if you have a book on a table and you want to push it to get it moving, static friction is what's going to stop it from initially moving. And kinetic friction is the friction when it's actually moving. So once the book's already moving and you continue to push it, now kinetic friction is acting on it. And so there's two constants, one of them for static friction, one of them for kinetic friction. Static friction is mu sub s, and kinetic friction is mu sub k. And this mu is just the symbol that we use for the coefficient of friction. So the maximum static friction is mu s times the normal force. So basically, friction force is equal to the coefficient of friction times the normal force. So as Mark mentioned, in an inclined plane, the normal force could be at an angle, and so the friction force will be the coefficient of friction times that magnitude of the normal force. And the same thing for kinetic friction, same thing for static friction. The only thing that we really need to know about the differences between the static and kinetic friction is that the coefficient of kinetic friction is usually always smaller than the coefficient of static friction. And you probably know this if you're trying to push like a bookcase, for example. It's a lot easier to keep it moving than it is to start it from moving. And that's because the coefficient of kinetic friction is less, so there's a smaller friction force. And so the last bullet point basically talks about a fridge. It takes some time to actually start moving. That's because the applied force has to overcome static friction, and once it's overcome, kinetic friction is the new force. And friction, like normal force, these two forces always attain the value that they need to be in a scenario. So what I mean by that is, let's say for a normal force, for example, let's say you have a 20 Newton block on a table, the normal force will be 20 Newtons. And if you replace that with a 50 Newton block, it'll be 50 Newtons, never less or never more. And the same thing for friction force. There's a maximum value. So let's say the maximum static friction value is 70 Newtons. And you push with 30 Newtons, the friction force will be 30 Newtons. If you increase that to 50 Newtons, friction will become 50 Newtons. If you push with 70 Newtons, friction will become 70 Newtons. And once you cross that 70, once you start pushing more than 70, static friction can only top at 70, so then it'll only remain 70. So now if I push at 90, it'll stop at 70. So it's kind of like, you can kind of think of it as peaking at the top.
Now we're going to go into free body diagrams, and when we talk about forces and when we're trying to solve for forces, it's really helpful to look at this type of diagram to help us organize our thoughts, draw on the forces, and also later on we'll explain this more, but help calculate the resultant force and also the net force. So to create a free body diagram, you first create a box, and that represents any object. You don't actually have to draw what the object looks like. And then you draw the arrows to show which direction the force is exerted towards, and also some sort of relative magnitude. So if the applied force is greater than the frictional force, or if the gravitational force is larger than the normal force, you should show that one is greater than the other, even if the ratios are not exact. That is not counted necessarily. And on the AP, you're expected to draw all of the forces from the center point, even though some people do teach it as where the force is originating. So for friction force, it'll be at the surface, but gravitational force will be from the middle. What else? And also, so you label the forces based on a standard sort of variables that we use. So weight or gravitational force is labeled with F sub G, normal force is F sub N, tension force is F sub T, and friction force is, there's multiple variations. Usually a lot of people use just F sub F for just frictional, and sometimes you can also be more specific and say F sub K for kinetic or F sub S for static.
I would just like to point out that usually this free body diagram that we've given a picture of, well, isn't really a good one. Usually you want all of the forces coming straight from the center.
Yeah.
And then pointing outwards in the direction that they're pulling or pushing the object.
Yeah. So you don't actually, so an important thing adding on to Mark is that you don't show what forces the object is exerting, but instead what is being exerted on it. And also, so this frictional force, that's the blue one, that would not be pointing like towards it. It would be coming from the center and from the center and showing outwards, if that makes sense.
Yeah, so what she means is the actual free body diagram will look something like this. You've got your force, just the applied force, F. Notice how they're all coming from the center. And then you've got mg, or just F sub g. And you've got your normal force. And then this way, of course, these aren't really that accurate. And then you've got friction. Notice how they're all coming out of this center point. In fact, sometimes you might just not draw the box at all and just draw the forces on the center point.
Yeah. So it might seem a bit overwhelming now with all the steps, but it almost becomes like second nature, because with basically any force related problem, you should draw a free body diagram just to help simplify the scenario.
Mm-hmm.
So, I don't know. Okay, sorry. The first answer is already up. But now we're going to talk about net force. And net force is basically just the vector sum of all the forces. And this helps tell us if there is an acceleration or not. And you've probably all heard the very famous equation F equals ma, and we'll go more into that later on. But it's very closely related to this idea of net force. And if the net force is 0, the object has no acceleration. And this means it's either at complete rest or it's traveling with a constant velocity. And if there isn't, yeah.
Oh, sorry. Usually when we say at rest, this is just a terminology thing. Usually at rest refers to equilibrium, and it's a little weird. At rest can refer to either it having no motion at all or it having a constant velocity.
Yes. Yeah, it could technically be more complicated physics, but in AP physics, you can just say at rest is like more traditional terms, like just sitting still to simplify the issue. But yeah, Mark is right. So yeah, so when we do net force, we basically, if you want to think about it, just add and subtract. So for A is already up, so we can just explain that one. So if you see that 40 is in this direction, and usually the right is positive and left is negative, that's more like the traditional method of doing this. So you have 40 minus 10, because that's in the opposite direction, which gets a net force of 30. And you say 30 newtons to the right. So why don't you give a shot at B and C, and then we can go over it, and then we'll go on to the next slide.
A couple minutes should be fine, right?
Yeah, I'm sure you guys can do this in a few minutes. Okay. So B, as you can tell by this one, is no net force. 18 cancels out this 18, and the 10 cancels out that 10. So no net force. And as we said before, this can either mean two things. It's either at rest or it's traveling at a constant velocity, so there's no acceleration. And for the second one, the two 10 newtons, which is horizontal, both cancel out. And the 18 newtons are left, and that's pointing downwards. So 18 newtons down. And now we're going to go into some practice problems. So if you have any questions, feel free to let us know now, or if not, you can just tell us in the chat later on.
So our first problem is going to be draw a free body diagram for a plane flying. Consider all forces, including lift, which is the upward force keeping the plane in the air, and drag, which is air resistance. There will be a few follow-up questions once we've drawn the the free body diagram. So, this just came to mind. Grace, do you want to draw the free body diagram for us? Show your understanding? It's fine if you don't want to. Okay. Okay. Well, this is our first problem, so I'll just draw it for you guys. Oh, okay. Yeah, that's fine. So, have you figured it out, though? Do you know what it should look like? Okay, so our free body diagram, oh, that's a really bad line. Oh, sorry, that wasn't supposed to be there. That was from, I'm just gonna, okay, so our free body diagram, we're gonna start off with a box. Always do gravity first, right? So we've got its weight. And its weight is gonna be whatever its mass is times gravity. And we're assuming that since it's flying, maybe there's a force from thrust. So we'll just call that F. That's just the force it's using to push forward. And then we've got lift. What should we call that? Maybe just F sub L. I don't know. And then since drag is really just friction, we'll just label that F sub F. And now, would you, Grace, do you want to tell us, or well, actually, never mind. I'll just ask the question first. If we consider that the plane is accelerating in this direction, in the forwards direction, here, my annotations went away. If we say it's accelerating with some acceleration this direction, what can we conclude about the force F and the force F sub F? I'll give you some time to think about that. No, not exactly, Grace. What acceleration? Since we know that we know that it has some acceleration, we know that this force has to be greater than drag. Does that make sense? Because we want there to be a net force here. If there's no net force, it can't have acceleration. But you did have the right idea.
Yeah, and just to clarify, F will talk about the relationship between the force and the acceleration of an object more next unit, but that relationship is through F equals ma. So F doesn't actually equal A unless, I guess, the mass is 1, which is really unlikely in most situations. So
even then, they're not equal because they have different units.
yeah, exactly. Yeah. So it'll be a very specific situation when they're exactly equal.
Yes, but here we just want there to be a net force. So we want F to be greater than F sub F for there to be an acceleration in this direction. And we can say the same thing if we want it to be accelerating upwards. If we have some acceleration, capital A, in the upwards direction, we know FL should be greater than mg. Does that make sense? Okay, good.
And no worries if
That'll
you don't
definitely be covered in more detail next week.
Yeah. If you don't get it now, it's
You'll
completely
get
normal.
it tomorrow, or you'll get it next week.
Yeah, and there's a lot of practice with forces throughout the AP,
Yeah.
so you'll be fine.
The next problem is just to draw an FBD for both M1 and M2 in this half-Atwood setup over here. And we're actually going to talk more about the physical calculations for this kind of setup next week. But for now, we just have to draw the free body diagram, so just label which forces are acting on it. As a small hint, the tension throughout a rope is always constant, so the tension pulling on M1 will be the same as the tension pulling on M2.
And that fact becomes incredibly important when we start calculations.
You think that was enough time, or would a few more minutes be helpful? Maybe I'll give it like 30 more seconds. Okay, so for this problem, we have two blocks and therefore two free body diagrams to draw. Let's start with M2 because it's a lot easier. So there's only the tension from the rope pulling it up and gravity pulling it down. There's only in the vertical direction, we can say. There's nothing in the horizontal direction. Actually, we don't know the full magnitude of the forces here, but so the arrows don't have to be exactly to scale or even the same. They should be like, I guess, relatively similar.
Well, we do always know the magnitude of gravity.
We do know the magnitude of gravity, but the magnitude of the length of the arrow compared to the tension forces.
Is unknown.
Yeah.
Yeah. So yes, this first diagram is not too difficult.
Yeah. For the M1, there's a few more forces. As Mark mentioned, gravity will always be straight down. Let me draw this in a different color, actually. There's gravity pointing straight down. And then normal force is always perpendicular to the surface. So it'll be at this angle. We don't actually need to draw the angle in the free body diagram, but we'll talk more about that angle next week when we deal with the accelerations of these blocks. And then we also have tension, again, the same tension pulling it this way. Now, friction is actually a bit of a tricky one. There's actually two ways that friction could go in this problem, depending on whether M1 is sliding down the ramp or sliding up the ramp. So maybe we should have specified, you could have put friction either way, but for this problem, we'll just assume that M2 is falling and M1 is going up the ramp. So in that scenario, let's say friction is, kinetic friction would be this way. But if you did put friction the other way, that's also technically right. Maybe it would have been helpful if we put some. I think it would be easier when we put numbers next week.
Yeah, but usually once you've drawn it here, you definitely move the free body diagrams off of the Atwood machine. That way you can better see what's going on.
Yeah, you probably draw a separate box, like outside the problem and do it.
Yeah, because this looks really cluttered and ugly.
Yeah.
Yeah. So does that make sense?
It's also worth noting that you don't split components in free body diagrams like shown here. There's many angles, but we don't draw an X and Y component in free body diagrams, even though we do use them in problems.
But once again, we'll talk a lot more about that next week.
Okay, so now problem 3, and this will be our last problem. A rightward force is applied to a book in order to move it across a desk at a constant velocity. Consider the frictional forces and neglect the air resistance. So why don't you draw a free body diagram for the situation, and we can reconvene in like 2 minutes-ish. So yeah, that should be okay. Okay, so for this one, a really key part of this is to understand constant velocity. And that sort of neglects the whole rightward force, because if it's at a constant velocity, you don't really have to determine which one's greater than the other. So that's how we get this drawing. As we mentioned before, there's always going to be a force of gravity pointing directly downwards. And in the same way, the normal force will be perpendicular to the surface, which I should have drawn, but we're just going to assume is completely horizontal, so therefore it will be perpendicular right there. And we also know that because it's going at a constant velocity, that the applied force and the frictional force will have to be the same. And that again neglects the whole rightward direction, because it doesn't really matter. Okay, does that make sense? Awesome. Okay. So we have some more sources at the end for some homework if you want to go for that, some videos, just things to practice to make sure you're more comfortable with the topics. And of course, we'll use them more and more as we go on with the other units. Yeah.